Hello everyone, welcome back. So let's recall the goal of variational autoencoders. So in this lecture, we will be going into the mathematical details of the variational autoencoder and we will derive the loss function corresponding to the variational autoencoder. So before starting that, let's recall the goal of our variational autoencoder. So the goal of variational autoencoder is to find a distribution q phi z of x. Please note that I have kept phi over here because we want to learn this parameter phi. That's why it is in the subscript. So it's q phi z of x is the distribution of some latent variables. So we are trying to find a distribution of the latent variables which is z, and they are q phi z of x, from which we can sample the values of z. So we will sample the values of z, we denote it by z superscript L. So we are sampling z from this distribution which we have to learn, and once it is done, we will generate new samples of x hat or x tilde here from p theta of x given z. Please note that theta is again a learnable parameter which we will do through neural networks. So let's see what this statement is saying. What this is saying is we have to learn this probability function, that is q of phi z given x. Once this is learned, then what we will do is we will sample this latent vectors z from this q phi z of x. So once they are sampled, and let's denote it by z of L, then what we will do is we will remove this network and then we will feed this sampled values into this network, that is p theta of x of given z, so that this network will generate x tilde, that are the new samples which are not available in the data set that is present over here. So if this sample is from a particular data set, this sample will belong to the same family but will not be in the same data set. And how this q phi z of x will be learned? It will be learned through the process of backpropagation. So once the process of backpropagation is done, then these neural networks which are defined by p theta of x given z and q phi of z given x will be learned, and the optimized parameters will be obtained in terms of phi and theta. So once they are done, then we will sample z of L from the learned distribution q phi z given x, and then the sampled values of zl will be fed into this generator network. So this is also called as a generator network. So it generates new samples. So that's why this is called as a generator network. So this is the goal of our variational autoencoders. In terms of graphical model, we can represent the same block in terms of this representation. Here z is the hidden variable and x is the observed variable. If the edge is moving from z to x, it is represented by p of theta x given z. So this is a generator network which actually represents this block. And if it is the other way around, that is if x is given and z has to be produced, then it is done through q phi z of x. So this is represented by this network, and this theta and phi are the learnable parameters that are learned through backpropagation. So this is the basic concept of variational autoencoders. So let's move into the mathematical details of this. So the derivation for the loss function can be solved through the problem of approximate inference. So what is this actually? So let's discuss that. Let x be a set of observed variables, that is this x we are talking about. So let x be the set of observed variables and let z be the set of latent variables. So what are they? So this is what we are talking about, that z is the latent variables. With the joint distribution p of z and x given, then the inference problem is to compute the conditional distribution of the latent variable, that is p z given x. So we want to find the conditional distribution p of z given x given the observations x. So our target is to obtain the conditional distribution p of z given x. As we have discussed also that our target here is to learn this conditional distribution q phi z given x. So that's why we are writing it over here. So that can be represented in terms of Bayes rule as p of x given z times p of z divided by p of x, right? So what's the problem with this equation? The problem with this equation is that it is difficult to obtain because the px which is in the denominator cannot be solved properly, and the reason for that is, you may recall from the law of total probability that it is equal to p of x given z dz. So we are actually marginalizing p of x out of this joint probability. So the reason for why it is not solved properly is because this integral, the integral which is over here, is not available in closed form or is intractable. Intractable means it requires exponential time to compute due to the multiple integrals involved for the latent variable z. Because you know the hidden latent variables can be of any size. In our case, when we discussed in our last lecture, the layer z was of 6 variables that were skin color, smile, something like that. So it was 6 variables. So for that 6 variables you have to have a 6 integrals here in order to solve this. It is hard to evaluate this multiple integral as the size of this latent vector z increases from 6 to 7 to 10 or whatever size we are taking. That's the reason it is highly intractable. And the second reason is that even this is also not available in a closed loop form. That is, the joint probability is also not available in the closed loop form. That's why the evaluation of px is very hard to do. So now we have found that the probability of x is difficult to obtain. Then how we can solve this problem, that is of finding the pz given x. So is there any other alternative for that? Yes, the other alternative is to approximate pz given x by another distribution q of z given x, which is defined in such a way that it has a tractable solution. So we will approximate this probability of z given x with probability of q z given x, and this q has the tractable solution, and this is done through variational inference. And the main idea of this variational inference is how to pose an inference problem that we have defined earlier as an optimization problem, and this is done by modeling p of z given x using qz given x, where qz given x has a simple distribution such as that of Gaussian. So we will try to approximate this problem as an optimization problem where we will substitute pz given x with qz given x, and where qz given x will be having a very simple distribution, and we know that one of the simple distributions are Gaussian. So what we will do now is we will try to evaluate the KL divergence between the pz given x and qz given x, and we will try to minimize that. What's the reason for doing that? So if you minimize the KL divergence between pz given x and qz given x, then it will approximate pz given x, because the difference will be nearly zero between these two probabilities. So that's the reason why we are minimizing the KL divergence. So as you may recall my earlier lecture, the KL divergence between the two probability distribution functions that are here, please note the subscripts over here, that is, one is of q of phi and the another one is having theta. So you have to keep track of this subscripts. So we are trying to find the KL divergence between a simple Gaussian distribution which is represented by q phi of z of x and p theta z of x, which is the one which you are trying to approximate. So the KL divergence can be written in this form as you already know. And what we are doing now is we are representing this in terms of the expectation. This thing also is very easy to understand now, as you must have learned my earlier lectures. On that basis, it's very easy to understand. So once this is done, you can again use the formula of log a divided by b is log of a minus log of b, and then you can obtain this. So once you obtain that, substituting a in b results in this expression. How this is obtained is by substituting this expression, that is p of theta of z given x, as this expression into here. So once you put it over here, you will obtain this expression, and this can be again simplified using the logarithmic identities into this. Please note that I have put the red ball over to the z. That means the z is being sampled from q of phi z given x. So expectation is taken over that z. That's why I have kept z over with a round curve, because it's very difficult to write over here. So that's the short form of actually z sampled from q of phi z given x. So since the expectation is over z and p theta x, that is this expression, does not involve z, it can be moved out of this expectation operator. So as a result of which we can move this log of p theta x out of the expectation operator, and once we move it out and take it onto the left hand side, we will obtain this expression, that is the divergence minus log of p theta x equal to this. So this is again the simplified expression of this expression. So let's move forward. So we will rearrange the equations and we will obtain this. This is obtained by just rearranging the terms over here, and that is done by taking a minus sign of the left hand side and the minus sign over the right hand side. So once you take the minus sign on both the sides, you will obtain this. And here you will observe that this expression is basically a KL divergence between the Q phi of z given x and P of theta z. So once you obtain that, this is the final expression you will obtain. So this is basically the objective function of the variational autoencoder, where the first term, this term, represents the reconstruction likelihood, and the second term, this second term, represents or ensures that our learned distributions Q, that is, this is the learned distribution that you will be learning through the neural network, are similar to the prior distributions that we will be defining. So this is actually the prior distribution that we will be defining, and your learned distribution should be similar to this prior distributions. So the loss function is basically minus of the objective function that we have written over here. So once you take the minus of that, you will obtain this expression, and this is what we were trying to prove in the very first start when we started this complete series of variational autoencoders. So this is the final loss function that we obtain for the variational autoencoder. So now you can see it's very simple to derive this once you know the concepts of probability and KL divergence along with expectation operators. So this is our log function which is defined over here, and you can observe this log function, and this log function has an inherent regularizer in it which is defined by the KL divergence and the reconstruction loss over here. So these are all inherently present in this log function. We are not putting it separately, that is, we are not putting an extra regularizer here by ourselves, but it is coming automatically over here. This is very good that we are obtaining a regularizer by deriving the cost function of the variational autoencoders. Normally in inverse problems, what we do is we will propose the regularizer by ourselves, but here the regularizer is coming automatically while we are deriving the loss function for this variational autoencoders. So now our target is to find the optimal values of theta and phi, that is theta star and phi star. As we already discussed that these are the weights of the neural networks that we have to learn, and these are the weights for the generative network, and these are the weights for the recognition network. So our main target is to learn theta star and phi star. So we have to do it through optimization framework, and we will do that by minimizing this loss function that is available over here. So before going any further, let's have a intuitive understanding of what this first term means and what this second term means. That is, the first term which we call it as a reconstruction loss, and the second term which we call as a regularizer. So we will understand this first, then we will move forward and see how to simplify this expression to the more simplest way. So let's have a more understanding of loss function. So we will try to gain some intuition about this loss function which is given over here, and we will see what individual terms of this loss function means. So as you can see, the loss function is basically dependent on theta and phi. These theta and phi are the network parameters that are to be learned. So that's why it's a function of theta and phi. The first part is basically the expectation carried out over to the log probability function given over here. Samples of z are taken from Q of phi z given x, and this Q of phi z given x is basically a neural network that is represented over here, and it's also called as a recognition model as you are mapping x to z. This we have already discussed in our earlier slides. So this is our neural network having the parameters governed by phi. So the first term is also called as log likelihood. Why it is called as log likelihood? Because if you take p theta x given z as a Gaussian function of having mean mu theta and covariance sigma theta, so when you take log of this Gaussian function, what you will get is a square error between the data sample and the mean of the Gaussian distribution. So let's discuss how we will obtain that. So let's suppose you have this p theta x given z given as this. So here you can see the covariance is sigma theta of z and mu is given as this. So this is the expression of a multivariate Gaussian as we have discussed earlier. Once you take the log of this expression, you will get a proportional term given by this. So this is basically a reconstruction error which is between x and the mean of z. So this is a basically squared reconstruction error. So this squared reconstruction error is also known as data fidelity term in inverse problem. So it basically tells how far your reconstructed data, that is x hat, is from the input data, which is this, that is z. So that's why this p theta x of z is basically given over here. This is theta actually. So this is also called as a generative model because it is taking input as this z vectors, which are the latent vectors, and it maps back to x or x hat, which is the reconstructed samples. So this is basically defined as a log likelihood. That is the very first term of this loss function. So now we will focus on the second term, which is basically a KL divergence between the q phi z of x and p theta of z. Please note, here we are assuming that we know this p theta of z, which is a Gaussian of zero mean and unit variance. So we assume it to be known. So what we want is, we want the probability density function of this to be close to that of this p theta of z. And this q phi z of x is basically given over here. So this is actually a recognition model that takes the mapping from x and produces the output z. So we want our data that is generated, that is z, should not be too far from the normal distribution, that is n of 0, 1. So that's why this is basically acting as a regularizer. It won't allow the latent variables to have distribution away from n 0, 1. So it's acting as a regularizer. So KL divergence not allows the PDF of the latent variables, that is q phi z given x, not collapse with that of zero variance, but penalize it if it deviates from 0, 1. So one more thing that I wanted to discuss is about this graph. So this is basically a latent variable space, and you are plotting these two as the q phi z1 given x and q phi z2 given x. So these are the PDFs around z1 and z2. So if you sample any data over here, then it will be actually a combination of z1 and z2. So whatever sample you take from this point will have a weighted combination of z1 and z2. So once you feed this data into this network, that is p of theta x given z, it will generate a data that is a weighted combination of z1 and z2. So that weighted combination of the z1 and z2, so that data will not be in the data set in which this z1 and z2 are present, because the data that is generated is basically z1 average of z1 and z2 divided by 2. So that's why it's a generative model, because it will generate data that is not in the data set in which z1 and z2 are present. So that's the reason why this diagram is over here. And these plots are basically the same plots that we discussed during the time of understanding these latent variables. So these are the Gaussian plots that we discussed during that time. So let's move forward. So this is another way of showing some insights to the loss function, and this is basically, we have a loss function which is basically data fidelity term, which we already discussed, plus a KL divergence term, which is a regularizer. So what we are trying to show here is that if the data fidelity term is only there and if there is no KL divergence term, what will happen? And if data fidelity term is not there and KL divergence term is there, then what will happen? And if both of them are there, then what will happen? So in the very first case, when the data fidelity term is there and if there is no KL divergence, what will happen is the reconstruction loss encourages the distribution to describe the input. So what will happen is our distribution, which is shown in the blue curve, will deviate from the prior, which is shown in black, to describe some characteristic of the data. So it will deviate from that distribution, that is n 0, 1 shown by black. But so the deviation will happen because there is no term to bring it back to sit onto the black Gaussian curve. So That's the problem if KL divergence is not there. The second case is when the data fidelity term is not there and if only KL divergence term is there. In that case, what will happen is that without the regularization, the network will cheat by learning narrow distributions, as you can see over here. So we will have a cheating going on over this side with narrow distributions of the learning, in which it may happen that the variance of this distribution will be very small. That is, with very small variance, this distribution is effectively representing a single value. So as you can see that you have a latent variable over here, so the distribution will be very peaky. It will not have a variance of 1 as it was in the case when KL divergence was there. So this problem can happen, and at this point our variational autoencoder will reduce to the normal autoencoders, because in normal autoencoders each point is represented by a fixed value. So if the variance is very small, very small, then it will just sit onto this z value. So that's why we need KL divergence, so that it should not reduce to the autoencoder case. That is the normal autoencoder case. So the third case is when both of them are there. So if both of the terms are there, then there will be attraction between the two distributions due to the first term. So this attraction will happen. That is, this curve, which is basically q phi z of x, it will attract towards this prior, which is n0, 1. So there will be an attraction and it will force it to move to this black curve due to the data fidelity term, and sufficient variance will be ensured. So it will have a fixed variance of some size, and that will happen due to the KL divergence. So KL divergence will force this distribution, that is the blue distribution, to have a specific variance, and it will not collapse to a very small variance. So in that case, the variational autoencoder will work properly. So here the black curve is basically our original distribution, and the blue one was our distribution, that is mu phi of x and sigma phi of x. These are the distributions that we will assume for our network q phi of z given x. So let's discuss how we can simplify this regularizer term, which we have defined in the last slide. So this is basically the regularizer term. So what we want is, we want an easy choice of this regularizer, that is the p theta z. So we take it as n0, 1, which is having a 0 mean and unit variance. And we want this p phi, no sorry, it's not p phi, it's p theta. So we want this p theta of z to be as close to this q phi z of x, which is unknown to us right now. So we want this to be as close to p theta of z. Why we want it to be as close to p theta of z? Because as we discussed here, if that is not the case, then it will turn into a case when it's a normal autoencoder, where it will learn a very small variance PDF, which is not desirable in case of variational autoencoders. So that's why we want this to happen, that is, it has to be close to n of 0, 1, having a variance not smaller than 1. Also, we could sample the distribution q phi of zx easily. So having p phi of z as n0, 1 also helps in another benefit, and that benefit is that if we want q phi z of x to be Gaussian with parameters given as this, where mu phi and sigma are the means and covariance, then the KL divergence has a very closed loop form. So we will obtain a very closed expression for KL divergence, that is given over here if we assume Gaussian for this and a normalized Gaussian for p theta of z, that is n0, 1. And what is that expression? That expression is this, and this is very easy to obtain. And how will we obtain this expression? This expression can be obtained by just substituting the parameters of this Gaussian and this Gaussian over here. Here we will put sigma 2 as 1, mu 2 as 0, and sigma 1 as sigma 1 x, phi x, and mu 1 as mu of phi x. So once you put that in this expression, you will obtain this expression. Here k, please note here k is the dimension of the Gaussian, and this is basically the trace function, which is summing up of all the diagonal matrix of this sigma phi of x Also we know that the determinant of sigma phi, which is basically a diagonal matrix, is a product of its diagonals. So above equation can be simplified as this. Here this is basically the summation over all the k dimensions of this sigma phi x, and this is obtained because the trace is basically the diagonal element summation. So we are summing up to k elements, that's why the sigma k is coming over for these elements. This is a scalar quantity, so we can just square it and sum up to k values. This is k, so we can replace it by this expression, and this is basically, we know that for the diagonal matrix the determinant is the product of its diagonal elements, so we will replace this determinant by this. So these are the diagonal elements of the sigma matrix with product in between. So it's a pi is basically the product of all the k elements. So this can be further simplified by pushing log inside this expression. So once you push inside the product, then the product will change to summation and it will be log of sigma phi of x. So we are just bringing out the summation k outside. So this is our simplified closed loop expression for the KL divergence, which is defined over here. Sometimes it is better to model sigma phi of x, that is given over here, as exponential of sigma phi of x for numerical stabilities. So in order to achieve the numerical stabilities, we have to do this substitution. So once you substitute this into this expression, the result will be this. So this is done just to have a numerical stability of the exponent compared to the log. So we are substituting exponential of sigma x instead of sigma x in the last expression to obtain this. So this is our expression. So final loss, that is the final loss of VAE, becomes this. So this is basically the simplified KL divergence. If we assume Q of phi z given x as a Gaussian having this distribution and P of x as this distribution. So on that basis, our KL divergence has a closed loop expression that is given by this. So now we have completed the complete derivation for this loss function and all the fine details for this are addressed. So the next target is how to carry out optimization of this loss function, that is how to carry out back propagation on this loss function, and we will see in our next lecture what are the problems during the back propagation process and how we can avoid them using reparameterization tricks. Thanks for watching my lecture. See you next time.